Hi everyone, welcome back to the third lecture of week 1 for Math 320. Before we get started, I will nag you once more by reminding you to do your exercises. The exercise sheet can be found on D2L. Last lecture, we talked about the size of sets. This lecture, we move on to something different, though still in the warm-up review stage of this course. We will talk about arithmetic properties of n, z, q, and r. Just a reminder, we will assume you know how to do basic arithmetic on real numbers. I will not ask you to justify things like associativity of multiplication or the distributive law when you multiply into a sum, though it is good for you to take a glance at the first 3 sections of the first chapter in our textbook to get reacquainted with some of the terminology related to arithmetic. In this set of slides, we first remind ourselves what sorts of arithmetic operations are allowed for each of n, z, q, and r. We start with the naturals. We can add and multiply the naturals, but we cannot, in general, subtract or divide them. I should probably specify what is the sense in which subtraction and division are disallowed. If we multiply two arbitrary natural numbers, we are guaranteed to always get a new natural number. Similarly, if we add two natural numbers, we are guaranteed to always get a new natural number. Since the type doesn't change, we say that the natural numbers are closed under addition and multiplication. On the other hand, if you have n and m two natural numbers and n is bigger than m, then trying to subtract n from m will give you a negative number, which is no longer natural. So the natural numbers are not closed under subtraction. Similarly, division will typically give fractions, and so natural numbers are not closed under division. The problem is partially fixed when we looked at the integers. Now the set is closed under addition, multiplication, and subtraction. Division, however, is still a problem, as you may get fractions which are not integers. The usual four-function arithmetic can all be performed for rational numbers. Such of things, non-necessary numbers, which can be made closed under addition, subtraction, multiplication, and division, as long as you don't divide by 0, are called fields. I will not give a precise definition of a field here, as for this course, we will not be proving anything starting from the basic field axioms. You can, however, see a discussion in Chapter 1, Sections 2 and 3 of our textbook, and you may encounter this concept again in a course in abstract algebra. Notice that the real numbers are also closed under these four operations, so the real numbers also form a field. In terms of arithmetic properties, Q and R both satisfy the same basic field properties. But if we go beyond basic arithmetic, R has certain advantages for analysis. One way to see this is that there are a lot more functions that make sense. Operations like taking the cube root, or functions like the trigonometric and logarithmic functions, cannot make sense as functions from Q2 itself, whereas we are familiar with their usual definitions as functions on R or on its subsets. A note on your homework: I will expect that you know how to do arithmetic, and I will not ask you to justify arithmetic operations using any sort of axioms. However, you should make a comment on your operations in two situations. First, when the operation forces you to change types. For example, when you are given m and n, two natural numbers, and you need to consider their quotient. You should either explicitly point out that the quotient is a different type, i.e. the rationals, or justify it if you somehow know that the quotient is in fact a natural number. Second, when you divide two variables, you need to justify why the denominator is not 0. Here we see that in terms of basic arithmetic, There's good reason to focus on understanding Q over looking at Z or N, but R doesn't seem to offer more in arithmetic. So why a course in real analysis? One justification is that there are many interesting and useful functions that cannot be studied if the only numbers that we have are the irrationals. But this will go beyond arithmetic. This is not so much a real justification. In fact, this can be regarded as a symptom of what we will talk about starting next lecture. Starting next time, we will be talking about the primary difference between Q and R from the analytic point of view. As was mentioned in the course overview, this is the concept of completeness. Until next time.